Okay, so everything is, let's review unit circle. So everything on unit circle is based off of these special triangles, either a 30, 60, 90 triangle or 45, 45, 90 triangle. All the quadrants are based off of these special angles. I have a handout if you want to review unit circle and trig identities and double angle identities. I'll hand that to you tomorrow. I forgot to make that for you guys. But as a review, there's really no need to memorize. I don't think you need to memorize your unit circle, as long as you know how to arrive at these values. Okay, and there's a little bit of a way that I guess in a sense is memorizing, but it's really just building it. All these ordered pairs are going to have 2 in the denominator. So if you guys can do that. So basically, if it's a test or quiz and you need to recall unit circle values, and here's a quick way to do it. So power 3, power 4, power 6, all the measures around unit circle are just based off of these ordered pairs, just the signs may be different. So you want to start here. Start at the upper left corner. Put a 1 down. And now you're just going to count or increase this number here. So 1, 2, 3. And then we're going to loop back around and say 1, 2, 3. All the numerators is going to take on square roots, except 1, because square root of 1 is just what? Just 1. So there's no need to put a square root there, but put a square root over all the numerators of the other values. Okay. All the ordered pairs are going to be cosine being the x and sine being the y. So your x value is going to correspond with cosine, your y value is going to correspond with sine. So if I asked you what is cosine of pi over 3, you would say what? 1/2. Okay. Sine of pi over 4. Yeah, root 2 over 2. What if I said sine cosecant of pi over 6? So cosecant is related to sine, right? So cosecant of pi over 6, we're looking at this number, and what do we do with it? Flip it. So cosecant of pi over 6 is what? 2. Anything in the second, third, and fourth quadrant, if there's a 3 in the denominator, you know it's going to take on those ordered pairs. Just the signs may be a little bit different. Anything with a 4 in the denominator across all fourth quadrants will take on these numeric values, root 2 over 2 and root 2 over 2. Anything in this with a 6 in the denominator will take on numeric ordered pairs of root 3 over 2 and 1/2. So if I want to find secant, I can just take the reciprocal of cosine. If I want cosecant, I can just take the reciprocal of sine. What if I want to find tangent? What's tangent? How can I use? Yeah, just sine over cosine. Or you can think of it as y over x. So if I ask you for tangent of pi over 4, what would you say? So I know it feels a little bit messy, right, to deal with a fraction divided by a fraction. So I think the better way to do this is you're going to do sine over cosine, but just cover up the denominator. Denominator is going to go away. So if you think of it as y over x, root 2 divided by root 2 is equal to what? 1. Yeah. What if I asked you for tangent of pi over 3? Yeah. Root 3 over 1, right? Cover up the denominator. Denominator is not going to be, it's just going to cancel out. So it's just root 3 over 1, which is root 3. Right. If I ask you for cotangent, cotangent is just the reciprocal, or think of it as cosine over sine. You see the x over the y. Okay. Now across your all 4 quadrants, it's nice to know what's positive and what's negative. So here's a way to kind of remember that. Okay, across your quadrants, I like to use this acronym here. Okay, maybe not a true statement here, but this one way to remember that is all students take calculus, ASTC. A means that all the trig functions will be positive in the first quadrant. S means that only sine and cosecant, because cosecant is the reciprocal of sine, only sine and cosecant will be positive in the second quadrant. Third quadrant just means that T means only tangent and cotangent will be positive in the third quadrant. So sine, cosine, secant, everything's going to be negative here. And then finally, the fourth quadrant, only cosine is positive. So cosine and secant. So tangent, cotangent, sine, cosecant, they're all going to be negative in this quadrant. So anything in the first quadrant is going to be positive, positive. Anything in the second quadrant is going to be negative, positive. Anything in the third quadrant is going to be negative, negative. Anything in the fourth quadrant is going to be positive, negative. So imagine just taking these ordered pairs and then just assigning the appropriate positive and negatives depending on which quadrant it's in. Okay, example 1, use these to find the value of all 6 trig functions at 60 degrees. $60 degrees is basically pi over 3. We know that any radian measure that we're looking for is always the angle times pi over 180. So if I want to convert to radians, I can just take that angle measure, 60 times pi over 180. 60 and 180 will reduce to be 1/3, so I'm just left with pi over 3. So anytime I want to convert from degrees to radians, I can just go through this little conversion here. But all in all, we're really not going to deal too much with degrees. Most everything we're just going to stick with radians. But we're going to practice writing out the trig ratios for pi over 3 for all 6 trig functions. So let's do that. All right, so see if you guys can fill out all these values. You know that sine pi over 3, you're going to just be building off of the y value, right? Cosine building off the x value. Okay, try that. Okay, so sine of pi over 3, 3 over 2. Cosine of pi over 3, 1/2. Tangent, just y over x, so root 3 over 1, root 3. Cosecant, we just take the reciprocal of sine. To make it more recognizable, we can rationalize the denominator. Secant is the reciprocal of cosine. Just take cosine and flip it, 2 over 1. Cotangent, either flip tangent or think of it as x over y, cosine over sine, 1 over root 3. Example 2, use these to find values of 6 trig functions at 225 degrees. 225 degrees, if I want to convert it to radians, it's times pi over 180. Reduce that, 225 over 180 reduces to be 5 over 4. Okay, if you think about this fraction, 5 over 4 is more than 1. We know that pi is basically 180 degrees, so 5 pi over 4 is a little bit more than pi, so it's going to be in the third quadrant, right? So third quadrant is going to be variations of pi over 4. You see the 4 in the denominator. You know it's going to be basically matched up with that order pair. What do you know about third quadrant order pairs? They're both negative. Okay, so this is all you need to look at to find trig ratios. See if you can do that. Okay, what's tangent of 5 pi over 4? Yeah, y over x, sine over cosine, cover up the denominator. You get negative root 2 over negative root 2. That just becomes 1. Cosecant, secant, cotangent, just flip the numbers that you see next to it. Secant, same result as cosine here with sine. Cotangent, I can think of it as x over y, or just flip tangent, which is going to be the same, right? Just still 1. Okay, questions so far? Okay, we're not going to do any graphical transformations, so you can cross out example 3 here. No period amplitude. Okay. But I do want to use the space to kind of remind us values of unit circle across the axis. So unit circle, we call it unit circle because our radius is 1 unit. Yes.
Can you go over?
Oh, right. So let me do it from this perspective. So we know that this is 0. We know this is pi over 2. We know that this is pi. We know this is 3 pi over 2, and this is 2 pi. Right. So your question is, how do we know which quadrant it's in? You look at the fraction, right? 5 over 4. What is that? Is that less than 1 or more than 1? More than 1. Is it less than 1.5? Yes. Yeah. So it's less than 1.5, but it's more than 1, so it's going to have to be in the third quadrant. So anytime you want to figure out what quadrant it's in, just look at the fraction, right? Don't worry about the pi. That's just there. It's going to be the same everywhere else. Look at the fraction and convince yourself it's a fraction less than 1/2, between 1/2 and 1, between 1 and 1.5, or between 1.5 and 2. And then you'll be able to know which quadrant it's going to land in. Okay. So all these values are just 1 unit away from the origin, left, right, up, or down. So I'm going to write those order pairs here. This order pair here is 1, 0. Order pair here is 0, 1. Order pair here is -1, 0. Order pair here is 0, -1. Okay. Cosine and sine still holds true. X value is cosine. Sine is y. So let me ask you a few questions regarding these special values here. What is cosine of pi? Yeah, look at the x value there, -1. Okay. What's tangent of 2 pi? Yeah, tangent, you know it's over here. You know tangent is y over x. 0 over 1 is a real number. 0. Okay. A few more examples here. Tangent of 3 pi over 2. Yes. Y over x, -1 over 0, undefined. Okay, cosecant of pi over 2. Okay, so we know pi over 2 is here. Where do we look if we want to try to figure out cosecant? Cosecant is related to what? Cosecant is the reciprocal of what? Sine, and sine is the y value. Okay. So what do I do with this 1 to get to cosecant? Flip it, right? What happens if I flip 1? Still 1. Okay. All right, one more here. Secant of 3 pi over 2. Secant is related to the x value. You're looking at the 0, but what do you do with the 0? I know the 0 is for cosine, so how do I get the secant? Flip it. So if I flip 0, what's that? It's 1 over 0, and 1 over 0 is undefined. Okay. So you're not memorizing any of this, right? You're just using what you know about order pairs, cosine and sine, and then just taking those order pairs and either flipping it or identifying it. Yes. pi.
-1. The 0 will give you.
Oh, 0. That's -1 comma 0.
Okay.
Yeah, -1, 0, 0, -1, 1, 0, and 0, 1.
And then you got the pi.
Oh, sorry. I just put an order. Those are just my locations. That's 1 unit away. That's just pi. Okay, we're just going to spend the rest of the time just solving trig equations. So I forgot to give you a sheet with all the double angle identities here, but sine of 2x is a double angle. We can expand that out. I'll write that expansion there. Sine of 2x can be expanded into 2 sine x cosine x. So I'll make a substitution, and then we can try to see if we can solve this equation. So if I want to solve this equation, maybe you're thinking, oh, I can just divide by sine and get an easier equation. So the careful thing we have to watch out for is we don't want to divide by a variable. If you divide by a variable, you're potentially losing a solution from your problem. So the way you want to move through this process is you want to bring it to one side and think in terms of factoring. So we're going to subtract one of these expressions over to the other side and then move through from there. 2 sine x cosine x minus sine x equals 0. So what can we do from here? Yeah, this is GCF, right? GCF of sine of x. So if I'm pulling a sine x out from each term, what I really mean by that is I'm dividing the sine x out. And whatever's left over is going to go into the set of parentheses. So if I take a sine x out, what's left? What's left? 2 cosine x, okay. How about here? Good, right? It's not 0, right? We don't want to make that 0. We want to think of it as, okay, if I cancel those out, there's still 1 left over. So now that we have factored form, we can set each piece equal to 0, and we can gather all the solutions. We're not losing a solution because we're not dividing that sign away. We're keeping track of it. Okay. We're going to look at we're looking for domain values between 0 and 2 pi. 0 is included, but 2 pi is out. So where is sine going to be 0? Anywhere else? Remember, sine is the y value here. Pi. There you go. Pi and 0. We don't include 2 pi because it's not included in our domain. Okay, solve for cosine x here. All right, so where is cosine equal to 1/2? But we also want to consider the other quadrants as well, right? Where else is cosine positive? Which quadrant? Fourth. So we're trying to find a variation of pi over 3 in the fourth quadrant. You know that's going to be over 3. You just have to find that numerator. So just keep adding 1 to the numerator until you figure out a fractional value that sits between 1.5 and 2. So 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. 5 pi over 3, right? 5/3 is less than 6/3. 6/3 is 2, so we know 5/3 is slightly less than 2. Yes, question.
Why is sine 2x equal to sine x?
Oh, sine of 2x is equal to 2 sine x cosine x. This is the double angle expansion for sine of 2x. Is that what you're asking?
But then you said equal to sine x, which means sine x is the same as sine 2x.
Well, sine of 2x is equal to 2 sine x cosine x. This is my identity that I'm using here. So I'm replacing sine of 2x with 2 sine x cosine x, and I'm just rewriting the left side into something that's more familiar. And then I'm starting my process from here. So in order to go through this process, I got to bring the sine x over to the left side, and then I go through my GCF and factoring. Yes?
But, I mean, first of all, how are they're still equal, right? Like they're the same thing. 2 sine x cosine x equals sine x.
Yeah.
Sine x cosine x equals sine 2x. I mean, how does that work?
So the issue is that it's tough to work in terms of double angle. Sine of 2x is not quite the same thing as sine of x. So we'll have an easier time work in terms of trig functions if we can get everything down away from double angle. So one of the trig double angle identities is that I can break sine of 2x down into 2 sine x cosine x. So that's just an identity that we're using to allow that left side to be easier to work with. So imagine that we're just rewriting it and we're really starting from this point. This is where we begin our trig equation solving process.
Yeah, but I guess what I'm asking is how is it possible that sine?
Well, for certain values, right? For certain values that could work. Like for instance, 0, sine of 2 times 0 is sine of 0. Sine of 0 equals sine of 0. And then sine of 2 pi over 3 is equal to sine of pi over 3 because sine of 2 pi over 3 and sine of pi over 3, they're both first and second quadrant, they both share the same positive y values, right? So certain values, they are going to line up. Right? Or if you think of it from a graphical perspective, sine of x has a certain period. Sine of 2x is a more condensed or stretched version, so they're going to intersect at certain spots. So we have 4 solutions, 4 places where, I guess you can think of it as where these graphs are going to intersect between 0 and 2 pi. So 0, pi, pi over 3, and 5 pi over 3. Uh, 1149. Okay. So I want to do a few more of these problems, but I want to just kind of do a little bit of a review here. Kind of talk about what radian is. We're dealing with radians. I want to kind of make sure that we have a kind of visual understanding what it means. So a radian is just the angle formed when the radius is wrapped around the outside of the circle. So I know that we feel like, oh, we have such easier time thinking in terms of degrees, right? Like what is a radian? So it takes 2 pi radians to get all the way around the circle. So it takes pi radians to get halfway around. This means that pi radians equals 180 degrees. So I have a little next page here just to kind of give you a visual feel for what a radian is. So let's say we have a circle. Okay. Circle has a radius. So imagine whatever the circle is, if you take that radius and if you put it on the outside of the circle, and if you were to fold it along the circle, that degree or that measure is 1 radian. So if you look here, 1 radian, 2 radian, 3 radian. So that's basically pi. 3.14 pi, 3.14 radians is pi, and pi is 180 degrees. Pi will take us halfway around the circle. So that's what radian is. Radian is just taking the radius and just folding it along the circle. So the reason why 2 pi is 360 degrees is because if you were to take that radius and kind of let it fold across the circle, there's going to be 6 radius and change that can make its way around the circle. Okay. So that's all radian is. It's just taking that radius and just kind of making it fold across the circle. So that's why pi and 180 is the conversion rate. 180 degrees is pi radians, and so if I want to convert from angles to degrees or degrees to radians, I just use that pi over 180 or 180 over pi to kind of get from one version to the next. But ultimately, we're just not going to do a whole lot with degrees. Most everything we're dealing with is just in terms of radians. Okay, let's try number 31 and 34 on page 7. Okay, we're going to solve for theta, but first let's try to get sine by itself. I'm going to divide by 2. Take the square root of both sides. And we get plus or minus. Now, plus or minus 1 over root 2. Maybe it's more easily recognizable if we were to rationalize that denominator. So if I were to take that 1 over root 2, basically plus or minus root 2 over 2. So that feels more recognizable, right? Sine of theta is equal to plus or minus root 2 over 2. All right, so where is sine equal to root 2 over 2? Yeah, all the angles over 4, right? So we list them out. You just basically have to add 1 to the numerator, but make sure that if it lands on the axis that we don't include it, right? So pi over 4, 2 pi over 4 is not quite second quadrant. 2 pi over 4 is pi over 2, so we skip that one. 3 pi over 4, that's 3/4 is less than 1, but greater than the half, so that's second quadrant. We increase this by 1, 4 pi over 4, that's not quite it, right? That's pi. We go again, 5 pi over 4, that's more than 1, less than 1.5, so that's third quadrant. 6 pi over 4, that reduces to be 3 pi over 2, so that's not it. Next up, 7 pi over 4. You know 7/4 is less than 8/4, which means that it's in the fourth quadrant. So I hope you don't feel like you have to memorize these measures, right? You're just adding fractions and just comparing it with, is it between 0 and a half, between a half and 1 between half and 1, between 1 and 1.5, or between 1.5 and 2, right? And then if you just have some ballpark fractional values in your head, that's not too bad. Okay, last one here, 34. 2 cosine squared theta minus cosine equals 1. I know the temptation is you want to factor out the GCF and set equal to 1 and go from there. But we can't set parts equal to the other side if it's not a 0. So I have to bring that 1 over before I can do anything. Okay, 2 cosine squared minus cosine minus 1 equals 0. Does that remind you of anything? Say again? What about factoring? Does that remind you of anything with factoring? So let me ask you this. What if we were to do an easier version of this problem? Okay, does that feel more recognizable? So if you feel like you can write this in terms of an easier problem, you can factor the easier problem and then bring the cosine back into the problem, right? If you don't want to factor in terms of cosine, then factor in terms of x, do something that you recognize from algebra 1, and then we can bring back cosine. So we can factor this, right? Multiplies to be -2, adds up to be -1. That's going to be -2 and 1. We got to deal with the leading coefficient, so divide by 2. The first fraction can reduce. The second fraction does not. I can pull that 2 out in front. So if we can factor this problem, then now let's bring back the messier variable, which is cosine. And now we're in a position to solve for x. So if factoring in terms of trig feels too daunting, then create an easier problem to factor in and then bring back the variable. So we set cosine of x minus 1 equal to 0. And then we also set 2 cosine of x plus 1 equal to 0. Solve for cosine of x, subtract 1, divide by 2. Okay, where's cosine equal to 1? Okay, 0 and 2 pi, but because 2 pi is not included in our domain, just going to be x equals 0. Okay, where's cosine equal to variations of 1/2? Over 3. But cosine negative is which quadrant? And fourth is a positive one. Second and third, right? So just think of fractions that land in the second and third quadrant. So 2 pi over 3 and 4 pi over 3. There we go. Okay. Your homework is from the handout, which is on page 5 and 6. So it's in your packet. I think I have solutions for them. I'll try to send them out today if you want to check your work with that. So page 5 and 6, you see the appendix worksheet here. Your homework's going to come from this page. Have a great day, guys. Thank you. Yeah, wrap it.
Like, still, you were allowed to do that. So you didn't have to
Thanks, Abel. Have a good day.
Here the 2 days after Thanksgiving break, so would it be better for me to take a quiz then or like this Friday?
Say it again?
I won't be here the 2 days after Thanksgiving break.
Oh, yeah, just take it afterwards.
Okay.
Yeah, okay.
So would I take it? Because I'm on a flight that's like late that Tuesday, so I don't know.
Yeah, just whenever you can
Okay,
take
so
it.
should I take it that Thursday?
Yeah, sure. Okay.
Thank you.
Mm-hmm.